Okay, so today I'm going to talk about, as Bart already mentioned, about FLORIDyn, which is a fast-running dynamic wind farm model aimed for control. And one second. We're going to talk first about the motivation behind the project, and then we're going to look into the three major stages, and also from these major stages, just looking at the key ideas of how this model has developed, and then we'll look at a showcase of the model itself. So first of all, looking at the motivation. A topic that we're probably very familiar with is that we have multiple wind turbines standing behind each other. The first turbine extracts energy from the wind and leaves a trace of slow wind speed behind itself, which a second turbine is affected by. So the second turbine has a decreased energy generated. And if the first turbine now takes the second turbine into account and adjusts its running behavior, then the second turbine can generate more energy because it's not standing in the wake anymore. And in total, the wind farm can produce more energy. This is something that engineering models have had quite some success with. Mainly FLORIS, which is the flow, redirection, and induction in steady state model. And these predict how these wakes will behave based on analytical equations, which are very fast to compute. So in a short time, we can find good set points for our wind farms. And this computational cheapness is needed because this is what our reality looks like. We have large wind farms where there's a lot of wind turbines standing in each other's wake, and we need to somehow master this complex aerodynamic interaction and try to find optimal set points for these wind farms. However, our reality also looks like this. So we don't always have homogeneous conditions. We can have different wind speeds at different locations in our wind field. We also have changing wind directions, changing wind speeds. And that is something where FLORIS models tend to struggle a bit as they're built for steady state. And this is where FLORIDyn comes into play. And we're trying to add the dynamics again to the engineering models, which has been approximately or lost at the start of the design. The first FLORIDyn model is based on the zone FLORIS model. The name comes from the fact that this wake is divided in different zones, so 6 plus the environment. And each of these zones is described by a border. And then within these zones, we have a description of the reduced wind speed. If we now misalign the turbine, the model tells us how the wake will behave based on that. And the key takeaway here is that all we need to do in order to calculate this wake is we need the downwind distance, then we get the deflection based on our turbine state, so yaw angle in this case, and the actual induction. And then we can calculate our deflection. And from there, we can also calculate the boundaries of the zones. So our idea is that every time step, we're going to create little traces called observation points. And these observation points are going to travel along the edges of the zones we have defined in the model. And since our computation is so easy, we can just let them run downstream based on only the state of the turbine at the time when they were created, a set of parameters describing the wake, and then their own downwind distance, which increases over time as they travel with the wind. And this returns then the full description of the wake in the dynamic sense, where we have all these observation points trying to describe how changes at the rotor plane will propagate downstream. Implemented, it looks like this. So on the top, we have SOFA, which is a high fidelity simulation, and it's used here as a validation tool. And at the bottom, we have the zone FLORIDyn model, where we can see that from the left starting, we have orthogonal aligned turbines with the main wind direction. And then in the second step, we see that the first turbines have changed their angle, their alignment with the main wind direction, and then how this changes propagates through the wakes and then affects downstream turbines later. Plus points from this model is that we have a quite intuitive extension of the FLORIDyn model that we initially used. It certainly succeeds at including dynamics. It has a low computational cost, and it was also used by Peter Gebrat to successfully close the loop with the high fidelity simulation. On the downside, we have that we're using a quite basic FLORIDyn model, especially now that we have quite an advancement since this paper came out. There's also a quite expensive wake interaction interpolation happening between the turbines, and there is a strongly simplified wind field condition, mainly that we have a constant wind direction. The model has been published in this first paper, the first source, and in the second source, and the first source is the FLORIDyn model that's been used if you're interested. This led to the Gaussian FLORIDyn model, and this is where my work starts. So what we've done is we have replaced the zone FLORIDyn model with the Gaussian description by Basanka et al. And have also made a change that we now make a distinction between the wake behavior and the dynamic behavior. So observation points still get created at the turbine and then travel downstream. And in steady state, we have the same behavior in the top where there's the wake system, and then in the down, which is the world coordinate system. But then if in the world coordinate system, we have different wind directions or changing wind directions, turbulences, then the observation points travel according to the wind directions. But in the wake coordinate system, they only still travel downstream. We've copied the approach to approximate the entire wake area with many observation points. And what this looks like implemented is like this. On the left side, you see the entire 3D wake, which is also a novelty of this model, where we have the observation points traveling downstream from 9 turbines. On the right side, you see SOFA again, here also used as a validation. And during this simulation, we do change the wind direction by 60 degrees. So on the right side, you see a slice at hub height, and you see how on the top we have at 700 seconds, how the shifting of the wind direction starts, and then 800 seconds progresses, and 900 seconds, it's already at the new wind direction. The gray arrows indicate the current wind direction, but you also see that the wakes still need to settle just alike as they have to do in SOFA. Plus points of this model were that we adapted the approach for heterogeneous and changing wind conditions, and that we included 3D flow effects like wind shear. We've used a more sophisticated FLORIDyn model and reduced the interpolation cost by saying that we can allow a nearest neighbor interpolation due to the high number of observation points. We've also improved the FLORIDyn interface by starting to do a segregation between the dynamics of the flow field and the used FLORIDyn model. Negative points are that we have a large number of observation points, which really drives the computational cost up for a larger number of turbines. And since our goal is to do wind farm control for realistic wind farms, we also need to look at numbers like 50, 60, 100 turbines. And the observation point behavior is still dependent on the used FLORIDyn model. Here, source number 3 describes this new approach and is currently in review. So you can already download and read that. There's also source number 4, which is the Gaussian FLORIDyn model, which is used for this model. This leads then to the final stage, or the current stage. I wouldn't say final, but the current stage of the FLORIDyn model, which is the FLORIDyn Framework. What we've done with the framework is we've taken the major negative point of the last model, which is the large number of observation points, and reduce it to its absolute minimum, which is 1 row of observation points. This row of observation points is now traveling down the center line and extrapolates from its position. So if we want to know the influence of the wake at a certain location, marked here by this yellow marker, then we're going to interpolate between the observation points that we have to create a ideal observation point closest to the location where we want to know the influence. And then we're going to create a vector from there to the point where we want the influence. We can translate this interpolation and vector system into the wake coordinate system and then ask for the influence of the wake. This also works in heterogeneous conditions, which is just what we introduced in the second version of the FLORIDyn model. But now we're doing the extrapolation instead of a nearest neighbor interpolation. And now the interesting part is that we can also do this with multiple turbines. So if we have the lower part, we have the world coordinate system, we have a yellow marker, and we have two turbines in heterogeneous flow. And then we do the extrapolation from the center lines of both turbines. Then we can create an effective wind farm, we're calling this temporary wind farm, at the location of the yellow marker. So this wind farm is only relevant for this one point and doesn't necessarily have to agree with the current layout of the wind farm, but it agrees with what the marker is experiencing at that time. Instant. And another advantage of this is that we can also ignore turbines which are not affecting this marker, which then reduces the computational cost. And this is an interface that is very easy to implement with existing FLORIS models, where we can just say, we're taking these effective wind farms and putting them into existing FLORIS models and ask them to evaluate them at this one point. And then we can just include existing models quite easily without having to implement them. The plus points of this model are the huge reduction of number of observation points, and also with that much improved computational cost. We've improved the coupling with FLORIS by really ensuring that the steady state is equal to the FLORIS model, as we're not doing another interpolation or extrapolation, but it is equal. And we've also improved the interface by using these temporary wind farms or effective wind farms as the interface to the FLORIS model. We've also improved the interface of sensors and estimators and how they can be included in the model, which we'll see in a second. The negative part is that we're now much more relying on extrapolation, and also something that that is more difficult is the validation. There is one source about this, the source number 5, which is the paper which is currently in review for the talk conference. There I'm going to dive a bit more into the inner workings and the mathematics behind the model. So if you're at talk, you can go that. I encourage you to listen to the talk there. And also a colleague of mine has done a sensitivity analysis in order to tackle tuning problems and validation. So also visit him. Looking at the showcase. So first we have a comparison between different models. Top left, we have SOFA, which is the high fidelity simulation we're currently still using as validation tool. At number 2, we have the FLORIDyn Framework, including an INI estimator, which is giving us the effective wind speed at the turbine locations. So we're using all 9 turbines as sensors in order to get the wind speed that they experience and have experienced in the past. And we're using the observation points in order to propagate this learned or gained knowledge downfield. On number 3, we see the pure FLORIDyn framework, where we're using the Gaussian model and no coupling to the high fidelity simulation. On the lower left side, we see the Gaussian FLORIDyn model, which was the second iteration of the model, where we have the nearest neighbor interpolation, so we get this mosaic-like effect. And on the right side, number 5, we have the FLORIS model as comparison, which would, in this case, just point straight downstream, which is not adequate to the situation the wind farm is in. Looking at the power generated, we're here looking still at the 9 turbine case. We're only looking at the 4 downstream turbines during the wind direction change, which is marked in gray. And as baseline, we could look at FLORIS, which is just changing with the wind direction. So there we see a quite symmetric influence that that comes and goes with the wind direction change, but we also do see that in our validation data from so far, which is here dotted, that the actual influence has a very different shape and is happening at a much later time than what a florist would predict under dynamic circumstances, which is not a quite fair comparison. But this is then where FLORIDyn shines, and you can see that in the very dark line, even the FLORIDyn model without the iron estimator, so without taking measurements from the field, we can quite accurately predict the dips and the times at which wakes influence downstream turbines. And then if we're taking data into account from the field, then we can also match the magnitude of the simulation. And here we have a film of the simulation, which is without the iron estimator, where we have a wind direction change starting at 600 seconds. And we can see how the winds, how the wakes start to shift and then settle again. And we also see here with the initialization, how the changes travel downstream, and then the wake becomes a steady state, so to say. Yeah. And then we also have the same with the iron estimator. So remember, we're using the turbines as sensors, and we're using the effective wind speed that they're experiencing. And this is very much work in progress, and we're trying to improve these results. But you can already see that we take the turbulent wind field, which is coming in, and we're capable of translating that into this parametric model. Now talking about the computational cost, because this is also what we are partially interested in if we want to use this model for real-time decision-making and control. The Gaussian FLORIDyn model is marked in yellow, and there we were struggling with the 9 turbine case, which you also just saw, which is here marked by the index number 1 of the 9T1 or 91T case. There we're getting to a computational time where one time step takes 1 second. And if you would have a time resolution of 1 second per time step for simulation step, then you're hitting real time. But with the new FLORIDyn framework, which is here just named FLORIDyn, we can see that even for 54 turbines, we can still stay at a very low computational time per time step, and can ensure then that we can optimize the inputs of all turbines in the wind farm into the near future. This was done on a laptop, on MATLAB. So we also hope that these computational numbers can be improved as we move to more sophisticated systems and a better implementation. And with that, I'm open to questions, and thank you for your attention.
Excellent, Marcus. Yeah, I really enjoyed your talk, and it's always nice to see the videos of these ideas play out. All right, I think we can move on to questions. So please raise your hand, or just ask a question in the chat. We can address that. Maybe to start with, I have one question. Can you linearize this model?
Yeah, that's a good question. That actually has been done. So the Peter Gebraat also used his implementation to implement an ensemble Kalman filter, or not an ensemble Kalman filter, an Kalman filter, and then used the current state and interaction as to derive then the Kalman gain matrix in order to correct the wind field states. And that's also something that we're going to explore into the future. So you can derive a quite easy state space model from the FLORIDyn environment and the setup. And then with that, of course, you can start using linear and nonlinear tools from classic control in order to to do all sorts of things with your simulation if you want to. Yeah.
All right. Thanks. Sebastian.
Yes. Thanks, Marcus, for your great presentation. Really nice results. Always nice to see such nice animations and videos. So thanks for that. One quick question: is the FLORIDyn model freely available? Is it on a GitHub repository? Can we just download it and run it and try it on?
Yes. So the revised model, which is here marked as source number 3, is publicly available on GitHub, and you can find the link in the paper. And there's also a little app that should help you to get started. The current version, the framework, is currently not publicly available, but I aim to have it publicly available by talk. Just need to clean up the code a bit, and yeah.
Thank you. And maybe one more question, if there's some time.
Sure.
So just for clarification, so you said something about INI estimators. So what you're basically doing is taking the measurements from local wind turbines to update as an input to your whole FLORIDyn framework as an additional measurement input to update the whole wind.
Yeah, so I think that's correct. So this plays into the greater scheme of wind farm control, where we have our wind farm and we have to align our model, which is in this case FLORIDyn, with the reality out there. So we're using FLORIDyn as a predictor, and we're feeding it with data from the turbines that we experience. This can be measurements, for instance, like the generator torque and the tip speed ratio, that then return effective wind speeds. And we can use these flow measurements in order to feed the FLORIDyn simulation, and therefore decrease the differences between the FLORIDyn simulation and the reality. And then hopefully we can use this estimated state and simulate it into the future. And if the state is close enough to our wind farm, then or wind farm state, real wind farm state, then we can make meaningful predictions. So then we get to the model predictive control framework that is then used for optimization.
Very cool. Thanks, Marcus.
All right, and then I see we have another question in the chat from Stikant. He asks on what platform FLORIDyn runs.
So currently the FLORIDyn code is written in MATLAB. Floris is available on Python, implemented by NRO, and there's also some MATLAB implementations out there. But the code that I've written that is also available is written in MATLAB. But we do aim to do a re-implementation in Python.
I think the concrete answer to this question is that you can run from both Mac OS or Linux or Windows.
Oh, yeah. Yeah, so it's not bound to an OS.
Cool.
Yeah.
All right, thank you. Does anyone else have a question for Marcus? Filippo, yeah, go ahead.
Yes, hi. Thank you very much for the talk, Marcus. Very, very interesting. I had two quick questions. One is, what version of Floris are you actually using? Because I know they're coming out with a new version that might be significantly quicker. So it's just as a question, is it 2.4 or is it the 3.0?
So the version that is used in this work is a version implemented just for this model. But the goal is to implement it also for Floris 3.0 in Python then. Yeah. But currently the MATLAB version is running with a MATLAB implementation of Floris. Yeah. But I also want to get this dependency, so to say, of this model and the framework. And this is, I think, something where the last version really helps by generalizing this interface And then hopefully we can also try different, more up-to-date FLORIS models, and not just the one that I now have implemented.
Absolutely, thank you. And just a second question, I know you mentioned control. Have you tested any control strategy with this? I mean, I'm guessing maybe wake steering could be the most suitable, but I was just wondering if you got to the stage of testing and maybe comparing different models or just the optimization results.
No, not yet. So the coupling still needs to improve on the software side. The only really working results that we currently have are the ones from Peter Gebrat. And the focus was also on wake steering. So the focus also will be, for my work at least, on wake steering. But induction control is also something that is interesting. And it depends on what the FLORIS models are able to predict. So I think there's a lot to be discovered too. But yeah.
Absolutely. Thank you. Thank you very much.
Thanks.
I have a question, if that's possible, but
yeah.
Yeah. I was wondering, because you show some results where you compare then FLORIS with FLORIDyn and SOFA, and then you show, okay, your model is quite capable of like estimating the SOFA data, but FLORIS is quite off. And I was wondering, because Enro is spending quite some energy in making FLORIS, then now if I look at these results, then I think to myself, well, why could FLORIS then still be interesting? Or is it maybe you would advise to go completely to FLORIDyn? I mean, how do you see that? What are your thoughts?
Yeah, so the way that I see it is, so I don't think the development of FLORIDyn will make the use of FLORIS obsolete in any way. I think both models have different time frames of value, so to say. So FLORIS has a quite high value, also paired with a very low computational cost. If you're looking at effects that don't change within hours or many minutes to days to years, where we can really predict wind farm behavior quite accurately over the course of a long time, where we can also do optimization of layouts and these way more calculation expensive tasks. And I think FLORIDyn will have value in more the seconds to minutes to tens of minutes scale, where we can see flow propagating through the wind farm and then see the reaction of the change of the wind farm to dynamic changes of the environment. Maybe also looking at floating wind turbines. There was a really interesting paper quite recently on dynamic models and their use for floating, how turbines might change positions based on the current set points and the wind directions and wind speeds. Yeah.
Okay. So it's a time scale difference. And that
I do believe so, yeah.
Okay, and another question is this FLORIDyn, how many state variables? If you, for example, have your 9 turbine case, how many state variables are we talking about?
So we have per turbine. So I'm just now talking about the latest version. So per turbine, it depends on how many observation points you choose. We use 200 observation points and a frequency of 4 seconds of simulation. And then each observation point has 3 states for its real world location, 3 states for its wake location, and then the wind farm states, wind field states. So this could be wind speed, wind direction, turbulence intensity, plus then these 2 states for the turbine states. So actually induction and yaw is also taken into account. So that is 11 states that are transported per observation point.
11 states in total?
Yeah, per observation point. So 11 times 200 per turbine.
Ah, yeah, okay. Okay, so yeah. then that's quite a big model you have already in there.
Yeah, definitely. So it is quite big, but also the calculations that we need to do only need to be performed on small sets of that data. So we don't have a huge complicated interaction between these states. But yeah, it is quite big. Yeah.
Yeah, but
you can also reduce the. Yeah, sorry.
you want to go to control, for example, I mean, then that becomes again a challenge, I guess. If you want to have, I don't know, a couple of hundreds of states in your model.
Yeah, that is true. But a lot of these states can be treated distinct from each other, so they don't necessarily have to be in the same system, so to say.
Ah, okay. Oh.
Yeah.
Cool. Nice presentation. Thank you very much.
Thank you for the question. Yeah.
All right. Thank you, Stuart. I think we have one more question, and then we'll round it up. We're running a little bit over time. Li Chuangfang asks, how do you assess the effect of kind of dynamic wind farm control on the AEP?
That is a good question, and I think we're not ready yet to answer it. So first we have to see in which situations models like FLORIDyn can provide value and where it can actually return an improvement over established methods like FLORIS. And then we also need to look at how often do these situations actually arrive in reality. So is that something where we profit off once every week, or is it something where we profit off 3 hours a day? And if we know these answers, and this can change probably also from location to location, but if we know these answers and have, then we can make predictions for the energy produced per year. But until then, I cannot say yet what the result will be.
Okay, excellent. Yeah, thank you, Marcus. All right, and with that, I want to thank Marcus again. I want to thank all of you for attending these talks. And a reminder that we have another talk coming up next week from Nikar Abbas, who's a PhD student at CU Boulder and also at NREL, and he's going to be talking more about wind turbine control and basically presenting a reference controller for fixed and floating wind turbines. So be sure to tune in next week again. All right, thank you very much, everyone. Have a nice weekend.
Thank you very much.